Welcome to Introduction to Building Codes, Bangladesh National Building Code 2020, abbreviated as BNBC 2020, Part 8, Building Services, Chapter 3, Building Acoustics. The description of our presentation today is designed to familiarize and assist code officials in locating, describing, and applying the applicable code requirements for building acoustics. Our course interview consists of the following information. Internationally, code officials recognize the need for a modern, up-to-date code that addresses acoustics in buildings, and that addresses the design and installation of these systems through requirements emphasizing performance. This presentation will cover key topics of the following areas. We will discuss purpose, scope, and terminology. This helps the code user determine the purpose of acoustic engineering, design, and installation of components within our buildings, the scope of certain buildings that must be provided with acoustics and references and regulations to sound transmission, and terminology. We will discuss specific terminology related to acoustic design and installation within our buildings. General considerations and provisions is also covered, as well as planning and design for noise control. Last, acoustical requirements in various occupancies will be covered additionally. The goal of this training is for you to learn and apply key code requirements contained in Chapter 3, titled Building Acoustics, to enhance your performance while inspecting these systems. This training will also provide participants with specific code requirements with examples related to design, installation, and inspection of building acoustic systems to further enhance your knowledge. Our course objectives today are as follows. Upon completion, participants will be better able to locate general topics in Chapter 3 regarding building acoustics, locate applicable codes and standards for specific situations, apply code requirements to real-world situations, explain the intent behind a given code requirement, use good judgment to identify certain systems related components as compliant or non-compliant. Chapter 3, Section 3.1, titled Purpose. The purpose of this chapter is to provide codes, recommendations, and guidelines for fulfilling acoustical requirements in buildings. A building acoustics code cannot be effective without adequate provisions for its administration and enforcement. Noise transmission can affect the quality of life of a building's inhabitants, and therefore the code official has the responsibility for establishing that these buildings where citizens work and reside are designed and constructed to address building acoustics. As you can imagine, if we were working in an office building and the mechanical refrigeration room, maybe a chiller room or other equipment, is adjacent to office spaces, this could provide many undue noises transmitting through the building's components and disturb workers while working. We will take a closer look at many of these sections and go through some design examples related to building acoustics, and requirements within this code. Let's take a closer look at specific sections related to scope and terminology requirements for building acoustical systems. Section 3.2, Scope. This chapter specifies planning, design, and construction codes, recommendations and guidelines on spatial, architectural, and technical aspects of acoustics within or outside buildings to ensure acoustical performance, comfort, and safety. Planning and design aspects are discussed generally and also particularly for buildings with different occupancies. This section describes the types of building acoustics covered by the code. The code is applicable from the initial design of the system through post-construction where performance is evaluated. Additionally, the scope of the code is primarily focused on building acoustical systems, those items specifically addressed in the code that make a building functional, comfortable, and safe. Section 3.3, titled Terminology. This section provides meanings and definitions of terms used in and applicable to this chapter of the code. The terms are arranged in alphabetical order. In case of any contradiction between a meaning or a definition given in this section and that in any part of the code, the meaning or definition specified in this section shall govern for interpretation of the provisions of this section. A code provision could be misinterpreted if the definition of a term as used in the context of the code is not understood. The following slides will provide key definitions that will assist the code user to properly understand certain terminology related to this chapter. Codes, by their very nature, are technical documents. As such, literally every word, term, and punctuation mark can add to or change the meaning of the intended result. This chapter contains several terms that are important to understanding the provisions of this code. Definitions are found both in this chapter and throughout the code. Let's look at some key terminology relating to building acoustics. The term dBA is a sound pressure level measurement when the signal has been weighted with the frequency response of the A curve. The dBA curve approximates the human ear and is therefore used most in building acoustics. dBA is therefore essentially a weighted scale for referencing loudness that corresponds to the hearing threshold of the human ear. It's a nonlinear curve that's referenced regarding decibels and frequency responses accordingly. There are different other scales that can be used, such as a C-weighted scale, a B-weighted scale, and a Z-weighted scale, but these do not reflect the human ear and the threshold for hearing of human ears. The next definition is frequency. The frequency of sound is the number of vibrations per second of the molecules of air generating by the vibrating body. One complete movement to and fro of the vibrating body is referred to as a cycle. Frequency is expressed as the number of cycles per second. It is also referred to its unit as hertz, abbreviated H sub Z. Impact isolation class, IIC, abbreviated. Impact isolation class is a single number impact insulation rating for floor construction. Tests are made with a standard tapping machine and noise level measured in 1/3 octave bands. These are plotted and compared to a standard contour. Below we see the picture indicating a tapping machine that has various octave bands. Reverberation, the prolongation of sound as a result of successive reflections in an enclosed space. When the source of the sound has stopped, is called reverberation. Consider a room with many hard surfaces that once a sound within the room is initiated, the sound essentially will bounce off of very hard surfaces for a prolonged period of time. This is called reverberation. The reverberation time, RT abbreviated, of a room is defined as the time required for the sound pressure level in a room to decrease by 60 decibels after the sound is stopped, and is calculated by the formula. The formula is RT equals 0.16 times V over A plus X times V, where RT is the reverberation time in seconds, V is our room volume in meters cubed, A is the total room absorption in meters squared, this is the unit Sabin, and finally X equals the air absorption coefficient. As you can see by the variables here, we are primarily concerned with the room volume, the total room absorption, and an absorption coefficient. Sound transmission class, abbreviated as STC, is defined as the following. To avoid the misleading nature of an average transmission loss, TL, value and to provide a reliable single figure rating for comparing partitions, a different procedure for single figure rating called sound transmission class, abbreviated STC, rating of a partition is determined by comparing the 16 frequency TL curve with a standard reference contour, the sound transmission class contour. STC ratings of some common walls and floors are given in Appendix E. Sound pressure level, SPL. The sound pressure level, or sound intensity level, is measured in terms of the unit Bell, abbreviated B, which is defined as the logarithm of the ratio of the sound pressure to the minimum sound pressure audible to the average human ear. The decibel, dB, is 1/10 of a bell. Thus, sound pressure level equals log to the base 10 of the quantity I over I sub O in bells, would equal 10 log base 10 of I over I sub 0 decibels. As you can see, it is 10 times the amount related to bells. Transmission loss is defined as the transmission loss of a partition is a measure of its sound insulation. It is equal to the number of decibels by which sound energy is reduced in passing through the structure. The units are decibels. As indicated below, if we have a partition that we are focusing on, and we have 110 decibels moving through this partition and a decrease of decibels to 45 on the outside of that particular partition. Now let's look at section 3.4 titled General Provisions. Specifically, section 3.4.1 titled Classifications of Building Acoustics gives us section 3.4.1.1 considering diversity of desired objectives and salient design features. Building acoustics can be broadly classified as three areas of analysis. Item A, acoustics for speech. Item B, acoustics for music, and acoustics for multiple sources or multi-purposes. This is a general classification which we will expand on through our discussion coming up shortly. A building or a building complex is usually a group of spaces or rooms intended for various functions. The requirements of section 3.4.1.2 provides that those spaces may require involvement of different types of acoustics as stated in table 8.3.1. For example, a school has spaces for speech. An example is classroom. Music, such as a music room. And multi-purpose, such as an auditorium. Thus, a building or a building complex shall not be generally classified as a whole for a particular type of acoustics. Rather, its spaces or rooms shall be classified individually, and appropriate acoustical design shall be considered accordingly. Let us look at table 8.3.1 showing the classifications of acoustics with brief description and examples of spaces involved. Table 8.3.1 is titled Classifications of Building Acoustics, Brief Description, and Examples of Spaces Involved. In the very first column, titled Classifications, we can see the three distinct categories. Item A is acoustics for speech, item B, acoustics for music, and item C, acoustics for multi-purpose. Our middle column, titled or described as Brief Description, describes the space adequately for acoustical requirements. Finally, the last column, Examples of Spaces, gives the code user an example of these particular spaces. As an example, if we use item A, acoustics for speech, the brief description gives us some general information about the space. As this relates to speech with foremost objectives of intelligibility, a space should have relatively lower reverberation time for speech. Generally, it covers narrow range of frequency spectra in lower mid-level, about 170 to 4000 Hertz for an average dynamic range of 42 dBA. The examples of these spaces are considered classrooms, lecture halls, conference halls, recital halls, assembly halls, courtroom, auditorium for speech, and similar examples of these spaces as well. The multipurpose, item C, gives us a brief description based on multi-purpose areas within our buildings. This includes both speech and music acoustics to fulfill objectives of both at a rationally compromised level. Acoustics design of multi-purpose space is quite challenging. As you can imagine, we need to fulfill both of the acoustics naturally occurring in music areas and other areas. We need to design, measure, and indicate different types of uses within these buildings. For example, there is a significant variation in desired reverberation times of a space for speech and music. Some of the example spaces are given in the last column. A multi-purpose hall, cinema theater, an opera house, a mosque for speech and melodious recitation, church, temple, etc. A note to the code user. Section 3.4.1.3 requires that spaces or rooms of buildings or building complexes having different types of acoustical requirements shall be designed in such a way so that they can coexist and work as a whole. This could take on several modeling, tests, and analysis to come up with this desired design for multi-purpose spaces. Section 3.4.2 is acoustical planning and design targets. Specifically, we move to section 3.4.2.1, a space involving either of the acoustical types in section 3.4.1, remember, speech, music, or multipurpose, must achieve few design targets. Some of these important design targets are mentioned below. Item A must be considered. Noise exceeding allowable limit should be controlled. Item B, speech intelligibility should be satisfactory. Item C, music should have liveliness, intimacy, fullness, clarity, warmth, etc. Item D, the design sound level must be optimum to be heard properly. Item E, diffusion of sound throughout the whole space. Finally, item F, there should be no defects such as echoes, flutter, echoes, etc. Necessary planning and design measures shall be taken for achieving these targets to optimum levels or standards as dictated by and in this code. This is given to us in section 3.4.2.2, particularly with respect to the planning and design measures. Continuing on with planning and design targets regarding acoustical design, among many following are the most significant factors affecting acoustical planning and design: noise, reverberation time, sound level, and diffusion of sound must be taken into consideration based upon the materials that are being used in the construction and analysis for these type of effects that sound can have within the room or space accordingly. Specifically, section 3.4.3.2 indicates that for various types of building acoustics as stated in section 3.4.1, The effects of these factors might be different. These factors are dependent on different conditions, like noise and sound level, room volume, building materials, surface materials, sound levels, room geometry, etc. As you can see, there are so many variables that affect sound based upon what the area is going to be utilized for, as well as many materials, the room volume, and geometry must be taken into consideration for the effective use of that room. As an example, notice these items in the picture, such as the geometry of the room, the height of the room, how the rear of the stage is shaped with respect to the front of the stage in order to project the sound outward, as well as the surface and finish materials on the walls themselves. General considerations and provisions for planning, design, assessment, and construction are stated specifically in section 3.4.4. Moving through this section, the very first section is 3.4.4.1. A reference is given here in Appendix F. A flow diagram summarizes activities required for planning, design, assessments, and construction related to building acoustics. We will be taking a look at Appendix F and the flow diagram coming up. Section 3.4.4.2 indicates that acoustical planning and design, including all parts and details, shall be performed during design phase of any project and must comply with standards and codes as dictated in this code. Periodically, the code will indicate other forms of design, guides, standards, and references, typically to the appendices. The designer must take this into account and design accordingly. Section 3.4.4.3, during planning and design phase, the expected results for acoustical performance of a space or a room or building, as dictated in different sections of this chapter, shall be precisely analyzed and assessed through standard practice. For example, precise computational methods based on computer analysis, simulation, and prediction techniques. Acoustical planning and design targets and expected results shall be clearly specified on the documents and documented as part of the design proposal. Appendix F, activity flow diagram, is indicated here on the slide, titled Planning, Design Assessment, and Construction in Building Acoustics. The flow diagram summarizes activities required for planning, design assessments, and constructed related building acoustics. As we will look at the flow chart, from the top on the left-hand side of the chart, it gives us the preparatory phase and identification of acoustics, planning, design targets, and a noise survey. We will cover this in depth coming up. When we move down to the second part, which is the design phase, this is where we get into the design phase regarding noise control, any type of background noise, reverberation time, noise amplification, and other variables that must go into the design. We then move to the assessment phase, such as standard practice like computational methods for analysis, simulation, and prediction with respect to our planning or preparatory phase and first design phase. We then move to the construction phase, peer supervision and assessment during construction. Finally, post-construction and the post-occupancy phase. As you can see, there are 5 distinct phases that the designer and installer must follow for proper building acoustic design and installation. On the slides that follow, we'll break it down into the various phases. The preparatory phase starts at the very top of the flow chart, where the engineer must identify the type of acoustics involved in the space. There's a reference to section 3.4.1. This is the area where classification of the building acoustics are indicated. We need to consider the diversity of the desired objects and the salient design features of the building acoustics. And they are classified as acoustics for speech, acoustics for music, and acoustics for multi-purpose areas. From that point, the identification of planning and design targets, strategy, standards, and codes comes in as part of the design phase as well. The reference here is systematically section 3.4.2, which covers acoustical planning and design targets. This is where we must achieve a few design targets. Some of the design targets included noise exceeding the allowable limit needs to be controlled. The speech intelligibility must be satisfactory with respect to the design. Music type classifications must have liveliness, fullness, and clarity. The desired sound level must be optimum to be heard properly, as well as any type of diffusion of sound throughout the whole space must be taken into consideration. There also should be no defects such as echoing, fluttering type echo, things of that nature. We need to take these into consideration, as well as the noise survey. We must be understanding and plan for, as well as design for, any outdoor noise control. We need to plan to control any outdoor noises from areas. If we are in parts of the country, like very heavy urban areas, traffic, street noise, we must be able to utilize this analysis to properly design for any transmission of those noises into our building from the outside inward. The design phase. From the preparatory phase, we now integrate our findings and analysis into the design phase part of the flowchart. In the design phase, the specific design criteria, strategies, and code requirements from the preparatory phase are put into play. This chart provides specific code-related criteria and relevant sections to find those criteria, which include the design of noise control for desired background noise, design for desired reverberation time, design for desired sound levels, design for sound diffusion at desired levels, as well as the design for desired speech privacy and sound amplification systems if applicable, as well as the design for compatibility with general design parameters, safety, energy efficiency, sustainability, etc. The last categories of the flowchart consist of the assessment, construction, post-constructing, and post-occupancy phases. During the assessment phase, the design is reviewed and further analyzed to verify the desired acoustical performance. If during the assessment, portions or all of the design are found to be incorrect or need modification, the project will go back to the design phase for correction. Once through the assessment phase, the project moves to the construction phase, where periodic assessment of the actual acoustic performance of the design is conducted. If during these assessments the performance is determined to not be acceptable, it will go back to the design phase again for redesign of non-compliant portions. In the post-construction phase, the final assessment is completed to verify the expected results from the design. Section 3.5, Planning and Design for Noise Control. Types of noise is specifically referenced in Section 3.5.1. Depending on the location of the source, noise might be of two types, as indicated in Section 3.5.1.1. Outdoor noise is given in Item A. The following area, some common outdoor noise occur in traffic areas as well as air traffic, road traffic, rail traffic, etc. The reference here is to see Appendix H. Item 2, noise from zones and buildings within built-up areas, machinery, appliances, construction activity, possibly loudspeakers, people, animals, etc. Item B, indoor noise. Following are some common source of indoor noise. Item B1, household appliances, machinery, footsteps on a floor, air conditioner duct, etc. We need to analyze each part of the indoor noise with respect to any type of adjacent machinery rooms. Even footsteps on the floor are addressed here, meaning that we must be understanding of the materials such as hard floors versus soft floor coverings that may be needed to absorb foot noises. Item B2, activities performed by occupants like people, pets, etc. Design sequence for noise control. Section 3.5.2. 3.5.1.1, in order to achieve noise control effectively, measures should be taken in the following order. Item A, suppression of noise at its source. If the designer or the analysis shows that there is a projection of noise at a source, this may be the area to provide some sound attenuation. B, layout planning is of concern as well. Simply by changing the layout direction, this may significantly reduce noise effects. Item C, insulation design, maybe by encapsulating the volume of the area with sound insulation. This may be an option with respect to noise transmission. Absorption design as well is indicated in item D. So there are various different sequences for designing noise control. A noise survey is indicated in section 3.5.3.4. A noise survey shall be conducted and a noise map shall be prepared to identify source type, intensity, frequency, and other parameters of noise in and around the site of any specific project. Noise levels should be measured for peak and off-peak hours of both working and holidays, and also for daytime and nighttime as defined in Noise Pollution Control Rules 2006 and its subsequent amendments by the Government of the People's Republic of Bangladesh. The reference here is to see Table 8.H.1 in Appendix H. The noise level shall be analyzed statistically for the following values. Section 3.5.3.5, a noise map shall be used to examine compliance to the permissible upper limit of noise levels set for different land use zones in the Noise Pollution Control Rules 2006 and its subsequent amendments by the Government of the People's Republic of Bangladesh. Again, the reference here is to Table 8.H.1 located in Appendix H. As references, intensity levels of some common noises are shown in See Appendix H as well, with reference to Table 8.H.3. Appendix H, specifically Table 8.H.1, titled Allowable Upper Limit of Outdoor Noise Levels. In the category of zones, we have the quiet zone, the residential zone, mixed use zone, commercial zone, and industrial zone. The upper limit of noise level in dBA is indicated for daytime and nighttime. The daytime range is given from 6 a.m. to 9 p.m. The nighttime range is given in the last column from 9 o'clock p.m. to 6 o'clock a.m. For a quiet zone, in the daytime interval between 6 o'clock a.m. and 9 o'clock p.m., we have an upper limit noise level of 50 dBA. The nighttime maximum upper limit noise level between 9 o'clock p.m. and 6 o'clock a.m. is an upper limit of 40 dBA. When we look to an example such as a residential zone, the daytime upper limit is given at 55 dBA, where the nighttime is decreased by 10 dBA and has an upper limit of 45 dBA. The commercial zone indicates a daytime upper limit noise level of 70 dBA and a nighttime upper limit of 60 dBA. This table allows the designer to provide the design for these particular categories of zones allowing upper limits indicated for daytime and nighttime operations. Another table indicated in Appendix H is Table 8.H.2, titled Typical Noise Levels Generated by Aircrafts. The aircraft manufacturer and model number is given in the middle column, and the flyover noise levels with takeoff, thrust, EPN, dBA numbers are indicated in the last column. As the example, the thrust that's given to us in the very last table is noise that is measured at 1.2 meters above the ground for aircrafts flying overhead at a height of 450 meters from the ground with takeoff thrust. The highest noise level among different variations in the same model is listed. As an example, the aircraft manufacturer and model, if we have an example, such as the Boeing 747, the flyover noise level with takeoff and thrust is given to us at 107.8 as a value. The Boeing 787, as another example, will give us a smaller, less sound transmission in the level of 99.6. Table 8.H.3, titled Subjective Evaluation and Pressure Levels of Familiar Sounds, is also in Appendix H. The description of sound is indicated in the first column, subjective evaluation in the second column, and the pressure level in dBA is indicated in the last column. As an example, the description of sound near a jet engine is subjective evaluation as deafening. The pressure level is 140 dBA. Another example may be a full orchestra with respect to a loud passage being played. The subjective evaluation would be very loud, and the pressure level would be 95 dBA. The description of sound near a freeway with respect to auto traffic. The subjective evaluation would be a moderate evaluation, and the dBA would be approximately 60 dBA. We can utilize this particular table for analysis and initial design considerations with respect to buildings that are being built near airports, near or with respect to orchestra areas, and near freeway auto traffic. There are many other examples here regarding the description of sound for the designer to look at and properly analyze based on the subjective evaluation, pressure levels, and specific description of sound as it relates to different areas indicated in this table. Section 3.5.3.6. The planning should be undertaken in such a manner that the noise can be kept at a distance. Quiet zones and residential zones should be placed with adequate setback from noise sources like airports, highways, railway lines, and factories. It might be useful to note that doubling the distance drops the sound pressure level by about 6 dBA. The correct placement of a building can eliminate many problems associated with noise control before they even start. This way, it's advised to the engineers to analyze the site thoroughly for this building placement along with the other designers that could eliminate any noise problems simply by the orientation of the building and their respective areas of use within the building. Let's consider a site where an apartment building will be located. The site is adjacent to a freeway and the sound located next to a freeway. At 5 meters from the freeway, the sound pressure level was measured at 70 dBA. How far away does the building need to be located from the freeway to reduce the sound to 46 dBA? Let's apply the general rule of thumb of a 6 dBA reduction every time the distance is doubled. At 10 meters, the sound level would be 70 dBA minus 6 dBA, resulting in a sound pressure of 64 dBA. At 20 meters, the sound level would be 64 dBA minus 6 dBA, resulting in 58 dBA. At 40 meters, the sound level would be 58 dBA minus 6 dBA, resulting in a sound pressure of 52 dBA. We need to go through one more iteration and evaluate the building being at 80 meters away, and the sound level would be 52 dBA minus 6 dBA, resulting in our value of 46 dBA of sound pressure. The correct answer is approximately 80 meters, given this rule of thumb. Following special provisions shall be applicable for air traffic noise. These requirements come from Section 3.5.3.11 of our code. Item A indicates that no building for human occupancy shall preferably be constructed where NEF value due to air traffic noise exceeds 40 EPN dBA. As a reference, typical noise levels of some aircraft types are shown in Table 8.H.2, Appendix H. This is a table that we previously visited a few slides ago. Item B, educational institutions, hospitals, auditoriums, etc., shall preferably be located at places where the value of NEF is less than 25 EPN dBA. In areas exposed to less than 90 EPN dBA, all of the windows shall be closed and properly sealed, having double glazing, in order to provide an acceptable interior noise environment. When we come to industrial and commercial activities generating high interior noise environments, might be located in areas exposed to noise levels greater than 90 EPN dBA. In airport areas of highest noise levels, sparsely manned installations like sewage disposal plants, utility substations, and similar other facilities might be located. Regarding road traffic noise, Section 3.5.3.12 provides us the following provisions. Item A, for road traffic noise level, the value of L10 shall be limited to a maximum of 7 dBA for zoning and planning new buildings in urban areas, while dwellings are proposed to have sealed windows. B, the maximum permissible upper limit of L10 shall be reduced to 60 dBA when the dwellings are proposed to have open windows. As you can see, there's a reduction in dBA. Item C. Major new residential developments shall preferably be located in areas where L10 levels substantially lower than those specified above. Where L10 is greater than 70 dBA, design solutions such as barrier blocks, noise buffers, or proposed built noise barriers shall be utilized in order to reduce noise levels at least to that level. Item E. Through traffic roads shall preferably be excluded from quiet and residential zones to avoid excessive traffic noise. And finally, item F. In the neighborhood of residential, educational, institutional, and healthcare buildings, legislative control shall be exercised for road noise, particularly from vehicles as dedicated in Noise Pollution Rules 2006 and its subsequent amendments by the Government of the People's Republic of Bangladesh. When it comes to rail traffic noise, Section 3.5.3.13 is referenced with the following provisions. Item A. No residential or public building except for the railway station and its ancillary structures shall preferably be connected to the railway lines. Item B. Mercantile or commercial buildings should not abut the railway lines or the marshalling yards. Only planned industrial zones may be located beside the railway tracks. Item C. In order to reduce the high noise levels produced at the arrival and departure of trains, platforms and railway stations shall be treated with sound-absorbing materials, particularly on the ceiling. D indicates the main platform floor shall be separated from the station building with a minimum gap of 50 millimeters so that the ground or structure-borne vibrations are not transmitted to the building. Item E. Windows and other openings shall preferably be placed as less as possible in the facade along the railway tracks. Item F. Greenbelts, landscaping, or any other form of barrier might be developed along the railway lines. Section 3.5.4 Planning and Design for Indoor Noise Control. The allowable upper limits of indoor background noise levels in dBA are shown in Table 8.3.2 and Figure 8D.1 in Appendix D. Design shall comply with recommended range of balanced noise criteria, the NCB curve, for different types of activity. The allowable upper limits of indoor background noise levels in dBA are shown in Table 8.3.2 below. This indicates in the first column the type of space, such as broadcasting and recording studios. The dBA would be 18, and if we plot this on the NCB curve, we would have a value of 10. The type of space, such as a classroom, a library, or even a small office, will give us a dBA ranging between 38 and 48. And the resulting curve, the NCB curve, would range between 30 and 40 on that particular curve. The background noise can vary widely based on the function of the building, but it's common for air conditioning systems and other building systems. As you can see from the table, in spaces that are sensitive to sound, such as recording studios, theaters, halls, etc., have a significantly lower allowable threshold for background noise than other spaces where background noise is critical or less critical. Shops, kitchens, lobbies, and other workspaces where speech is not critical. So this is based on the type of space, and this is the allowable upper limit values regarding these spaces indicated in tabular form. From Appendix D, a balanced noise criteria curve is pictured below, is used to specify acceptable background noise levels in occupied spaces. Instead of just a straight decibel pressure level, each decibel level is plotted over a frequency range. As you can see from the curve, at a lower frequency, a much higher decibel level of background noise is acceptable versus the same decibel level at a high frequency. The recommended sound insulation criteria are classified in some grades given to us in section 3.5.5.1. The STC value for airborne sound insulation is graded as stated below. We are also referred to figure 8.D.2 in Appendix D. Item A, grade 1. STC equals 55. Apply mainly to fully residential, quiet, rural, and suburban areas, and in certain luxury apartment buildings. This is grade 1. Grade 2, with a value of STC equals 52, apply to residential spaces in relatively noisy environments, typical of urban and suburban areas. Grade 3, the sound transmission criteria, express minimal requirements applicable to very noisy locations such as commercial or business areas like shop, houses with dwelling units on upper floors or downtown areas. The STC value, again, is for airborne sound installation. Pictured here is a sample of sound transmission class test. The test is conducted with a measuring device or devices in 2 rooms, one source room and one receiving room. The sound pressure levels in both rooms are compared at 1/3 octave band frequencies from 125 to 4,000 Hertz. The difference between the rooms is used to calculate the transmission loss at the various frequency bands. These transmission loss values, noted as ATL, in the table are plotted on a graph and then compared to standard STC contours. Whichever curve is most closely resembled is the STC rating that is assigned to the assembly. As we look at the graph, in the graph, the solid line is the transmission loss values plotted at the various frequencies, and the dashed line is the standard curve for a STC of 56. The following tables are located in Appendix D and provide the approximate range of airborne sound insulation and impact sound insulation required or recommended between dwelling units. Sound transmission class deals with transmission of airborne sound, typically through walls, while impact insulation class deals with impact sound, typically through floors. So we need to make a distinguishing mark between the two. With high impact sound, as indicated, in both cases, the higher rating signifies a better level of soundproofing. The grades of STC and IIC are also provided that align with the code. As we look at the tables and graphs as indicated here, we note in the first table we have our sound transmission loss in dB. The various grades are indicated towards the bottom of the table: grade 1, grade 2, and grade 3. This gives us the recommended sound insulation criteria that we find in section 3.5.5.1. As you remember, grade 1 apply mainly to full residential, quiet, rural, suburban areas, and certain luxury apartment buildings, where our grade 2 STC of 52 apply to residential spaces in relatively noisy environments, typically urban and suburban areas. And grade 3 with an STC of 48 will be in places that are very noisy locations, such as commercial or business areas, or with dwelling units on upper floors or downtown areas. As we see here, we have the approximate range of airborne sound insulation requirements or recommendations. We have our curves plotted on the frequency in hertz versus the dB sound transmission loss and the according values that are recommended in our code: 48, 52, and 55. Just like the sound transmission loss, the table and graph associated on the right-hand side is indicated with impact sound pressure level in dB. Grade 1, 2, and 3 are given again. Remember, this is for impact sound insulation requirements. This is normally in floors. This table, 8.E.1, located in Appendix E, provides STC ratings from various building elements that includes interior partitions, doors, windows, and masonry walls, including improvements, modifications that will provide additional ratings. Note from the table that masonry and concrete have higher STC ratings than other materials. Also note that with minor modifications, which could include but are not limited to adding an additional layer of gypsum board or adding additional insulation to standard construction methods, can typically provide acceptable level of sound transmission reduction. When we look at this particular table, it gives us a description up at the very top. However, at the top of the table, improvements in STC ratings of stud and partitions. There are two notes to the table that the code user must look at while applying the table. The first part of the table up at the top is a description, and it indicates basic partition. Single wood studs, 400 millimeter on centers, 13 millimeter gypsum board on both sides with an air cavity, would have an STC rating of 35. However, within this category of the basic partition, we could add to the basic partition by applying an extra layer of gypsum board either on one side or both sides. And we could add either 2 or 4 respectively, as well as the typical STC value for doors, the door category, door construction as indicated, down in the middle of the table to the left-hand side. For a typical louver door, that would have an STC of 15. Now remember, the STC is a value that is at a minimum, and we must provide the minimums required in the code, depending on whether it's a dwelling, a commercial building, if it's a quiet area or very noisy area. We will get the general minimum ratings from the code. We can build upon materials and then take the summation of all of the additive STC components and provide a composite type of wall. And when we look to doors, we look for something that is at least almost equivalent to the wall rating to provide that barrier for airborne sound transmission. As an example, using table 8.E.1 from the previous slide, design an improvement to STC ratings of stud partitions. Starting with the basic partition value of 35, increase the partition value to at least 46. Option 1. Let's try adding resilient channel supports over the studs and adding an additional layer of gypsum board to both sides. As indicated, we take the basic partition, single wood studs at a base 35 STC rating. We add double gypsum board to both sides. We can get a value of +4 and a resilient channel supports for the gypsum board, and we can also add an additional 5. The total, we take the summation. The total STC rating would then be 35 plus 4 for the double gypsum board plus 5 for the resilient channel supports for the gypsum board, and that would equate to 44, which is less than our needed 46. It appears we still need additional improvements. Let's look at the table again. Upon following the table and locating note B below, we need to apply this particular note. Note B says when using 2 improvements, add an additional +2. For 3 improvements, add +3. So for our particular method, we have 2 improvements, and we will add an additional +2 to our overall summation. Recalculating, the total STC rating for our assembly starts at 35 for the basic partition. We add 4 for double gypsum board on both sides. We add 5 for the resilient channel supports for the gypsum board. And then we will add another 2 based upon note B to the table. And that summation results in 46. That is at least equal to our proposed design of 46. Therefore, our design is acceptable. Let's look at another option. Option number 2, let's substitute metal studs in lieu of wood studs and add an additional layer of gypsum board to one side and install a single thickness absorbent material in the air cavity. When we do this, the first approach is to reference Note A to the table. And it indicates for application to metal stud partition, use adders in Note B, but begin with STC 40 for 90 millimeter basic partition. And this is what we are going to utilize. We're going to start with 40 in our equation and then take the summation of various values to add to the total STC of our assembly. So from 40, we add 2 for the double gypsum board on one side. We add 3 for the single thickness absorbent material in the air cavity. And then we add a 2 according to Note B of the table. Note B again indicates when using 2 improvements, add an additional +2. Therefore, our design is 47, which is greater than our resulting value previously of 46, and therefore the design is acceptable using metal studs with double gypsum board on one side and single thickness absorbent material in the air cavity. Another table, such as table 8.E.2, is also located in Appendix E and provides STC ratings for various occupancies and the spaces within those occupancies. The first column lists the different types of occupancy. The next column is the room within that occupancy under consideration, such as the main room, maybe loud rooms within the occupancy. The third room is the space or room that is immediately adjacent and separated from the room under consideration. The next 2 columns, quiet and normal sound isolation, respectively, are the STC values to be provided between the room under consideration and the adjacent areas. As an example, we will apply the table as indicated for the type of occupancy. In our case, let's go down the table to executive areas, doctor suites, confidential privacy requirements. The wall, partition, or panel between these particular rooms of an office, when we have adjacent to the office a corridor or a lobby indicated in the adjacent area column, the corridor or lobby, the sound isolation requirement background level in the room being considered, we have a quiet STC rating of 45 or a normal rating of STC 42. This table gives the designer plenty of information to specify the areas in which the building is going to be designed with these areas relative to quiet and normal STC ratings. This will aid the designer in specifying certain materials for the STC ratings. Using Table 8.E.2, determine the STC rating for the walls of the center classroom adjacent to the mechanical room, corridor, and classroom. Use the quiet sound isolation column for this particular design. In this example, let's assume we have a classroom located in a school, a mechanical room classroom, a corridor surround the classroom. From the previous table, let's determine the minimum STC rating for each wall. We need to start with the room under consideration to navigate the correct portion of the table. Once there, we need to look at the adjacent area and match it to the actual use of the adjacent area. Once we locate the correct adjacent area, we follow that row over to the sound isolation requirement. In this case, we are directed to use the quiet column. So that's the value we will select. The classrooms are indicated as the room being considered, as indicated in the red box. The adjacent areas to the classroom is an adjacent classroom. We will pick the STC value of 42 in the quiet column for the adjacent classroom. The corridor or public areas, we will pick the STC rating of 40, again in the quiet column. We move down to the lower level of the table to the mechanical equipment room that is adjacent to the classroom. And we will pick an STC rating of 50 for the classroom separating the mechanical closet as indicated. Impact noise problems can be controlled in the following ways, given to us in section 3.5.6.1. Preventing or minimizing the impact by cushioning the impact with resilient materials like floor tiles of rubber and cork, carpeting on pads with desired impact isolation class, criteria for airborne and impact sound insulation of floor ceiling assemblies between dwelling unit, tables 8.33 and 8.34. Item B, floating the floor for isolating the impact floor from the structural floor by a resilient element is extremely effective. This element can be rubber or mineral wood batts, blankets, or special spring metal sleepers. Item C, suspending the ceiling and using an absorber in the cavity. Item D, isolating all rigid structures such as pipes and caulking penetrations with resilient sealing. As we note and look at the picture below, we find that the picture is an area that is not sealed up. It has been left unaddressed in an assembly as shown. It will not allow an assembly to perform at an optimum level. This area would have to be filled accordingly. Table 8.3.3 titled Airborne Sound Insulation of Partitions Between Dwelling Units. This table gives us requirements for partitions in dwelling units. For example, consider two apartments A and B that share a common wall. A living room is located on the apartment A side of the wall, while a bedroom is located on apartment side B. I can locate this scenario in the table and determine the STC requirement. In this case, it is 54. Note that the STC is provided for grade 2. Per the note of the table, grade 1 or 2, if were desired, I would subtract or add the value given. Also note that per the note A, that if there is a situation where spaces overlap and multiple STC values apply, the strictest will govern the rating of the partition. Notes are effective to the table. Let's look at note A. Note A indicates wherever a partition wall may serve to separate several functional spaces, the highest criterion must prevail. And just above note A It indicates for grade 1, add 3 points. For grade 2, subtract 4 points. As we can see, the third column of the table is based upon grade 2 STC requirements. Table 8.3.4 titled Airborne and Impact Sound Insulation of Floor Ceiling Between Dwelling Units. This table is similar to the previous table, with the addition of values of sound insulation of floor ceiling assemblies between dwelling units. Like the previous example, assuming apartments A and B are located above and below each other, a living room is located in an apartment below a bedroom, in apartment B above. The table would be searched for this scenario, and we find that the required IIC value of 57. This value should be adjusted based upon the desired grade. As previously, we need to look at the notes of the table. The third column of our table and the fourth column, as seen here, are based upon grade 2. Grade 2. And again, the notes to the table, if we desire to grade 1, we must add 3 points. And for grade 3, we must subtract 4 points. Item A, or note A, again, the arrangement requires greater impact sound insulation than inverse, where a sensitive area is above less sensitive area. Protection against the effects of noise exposure is given to us in section 3.5.8.1. We must protect against any type of noise exposure, provided when the sound level exceeds those shown in table 8.3.5. Now, 8.3.5, the table is given to us below. The table is indicated as permissible noise exposure. In the first column, gives a sound level in dBA, which is a slow response. It ranges from 85 to 97 dBA. This is permissible noise exposure. The duration is given to us in the second column, duration per day in hours and minutes. The permissible noise exposure at 85 decibel and duration per day would give us 16 hours, 0 minutes. Whereas if we go down to 97 dBA, we have the duration per day at 3 hours, 2 minutes. The notes to the table give some clarity. The sound level should be measured on A scale at slow response. And item 2 will give us when the daily noise exposure is composed of 2 or more periods of noise exposure of different levels, their combined effect should be considered rather than individual effect of each. Section 3.6, Reverberation Time, Sound Pressure Level, and Diffusion of Sound. General considerations are given in Section 3.6.1. A, for an overall performing, comfortable, and safe acoustical environment, along with the issues of noise, other significant aspects of acoustics should be considered. This shall include sound pressure level, reverberation time, and diffusion of sound. Speech intelligibility is a significant parameter to achieve satisfactory acoustical design. Percentage syllable articulation, or PSA, is an index for assessing speech intelligibility. PSA can be expressed as the following. For English language, PSA equals 96 times the coefficients for average speech level as indicated in percentage. For Bangladesh language, PSA equals 93 times the coefficients for the average speech level. The speech level, PSA, and liveliness indicators and coefficients can be determined from Appendix I, Figure 8.I.1 in Appendix I. These tables are located in Appendix I and provide the curves to determine speech level coefficients, reverberation, time coefficient, and noise level coefficient for the use in determining the percentage syllable articulation, or PSA. As we can see, curve A has a solid line, which is a speech level coefficient. The dotted line is the PSA versus speech level. Curve B gives us the reverberation time coefficient, K sub R. Curve C gives us the noise level coefficient, K sub N. Solid line is the speaker and listener in noise. The dotted line is only listener in noise. As an example, determine the speech level, reverberation time, and noise level coefficients given a sound level of 50 dB speech level, a reverberation time of 1 second, and a ratio of noise to speech level of 0.4, only listener in noise. The first curve, A, we take the sound level in dB of 50. We rise up vertically until we intersect the curve. Once we intersect the curve, we move horizontally to the right and find that particular value around 0.97 as our loudness factor. That would be K sub I as a coefficient. The next, curve B, reverberation time coefficient. We need to find K sub R. We take the reverberation time in seconds given to us as 1 second, move up vertically until we intersect the curve, move horizontally to the left, and again we have a value of 0.97. This is our reverberation time coefficient, K sub R. Last, we have our noise level coefficient, K sub N. We need to go to the dotted line. This is for only listener in noise. We have a ratio of noise to speech level given to us of 0.4. On the x-axis, we find 0.4 rise vertically to the intersection of the dotted curve, and we move horizontally to the left, and we read K sub N at 0.85 as our coefficient for ratio of noise to speech level. Coefficient. Section 3.7.2.1. For speech sound, a descriptive scale is shown in Table 8.3.6. This provides a system of ranking the relative quality of sound isolation. The relative quality can be ranked 0 to 6, with 6 being total privacy, where a shout is barely audible, and a 0 providing none, which is a normal voice level, is always intelligible. As we see, the table is made up of the ranking in the first column from 6 down to 0. The descriptor is given in the second column for total privacy at a ranking of 6 and none as a ranking of 0. The hearing condition is indicated based upon the ranking and the descriptor accordingly. For a ranking of 6, shouting is barely audible. A ranking of 5 would be excellent. Normal voice levels are not audible. Raised voices barely audible but not intelligible. As we go down from 6 all the way down to 1 as a ranking, this would be a poor descriptor, in which case our hearing condition would be normal voice levels are audible and intelligible most of the time. Relation between barrier STC and hearing condition on receiving side with background noise level at NC-25 is shown in Table 8.3.7. This is given to us by the requirement found in Section 3.7.22. Whereas this table provides various barrier STC ratings, the hearing condition associated with them, the ranking, and the space or applications that should be applied. For example, if I were a designer and looking for a hearing condition in which loud speech could be heard, but not normal speech could not be understood, I would start with a barrier in the 42 to 45 range and refine the design from there. Note that several recommendations and requirements are contained in the code regarding STC for partitions beyond this table. As we can see here, specifically in the table, we have other STC barrier ratings as well. I can use a barrier of 30, which would give me a hearing condition of loud speech can be understood fairly well. Normal speech can be heard but not easily understood. Our descriptor and ranking would be fair, and the room divider where concentration is not essential. This would be our application in our very last column. So again, this table can be used with respect to design of different areas within our building based upon speech intelligibility. Figure 8.J.1, Appendix J, shows speech privacy analysis sheet, which shall be used to determine speech privacy rating number for design of enclosed space. We can find the reference here from Section 3.7.3.1. As we look at this, we expand the explanation of the table based upon the speech privacy analysis. We have speech rating, isolation rating, speech privacy rating number as well. That goes into the table. We have a source room factor that gives the approximate effect of the room absorption on the speech level in the source room. The scale in figure 8.J.1, Appendix J, represents average absorption. For live rooms, the factor should be raised by 2 points. And for dead room, the factor should be lowered by 2 points. Factors A plus B give the approximate source room voice level. Privacy allowance determines the measure of privacy required as normal privacy and confidential privacy. Isolation rating of the receiving room, room number 2, the STC rating of the barrier. See tables 8.E.1 and 8.E.2 in Appendix E. The noise reduction factor indicates the receiving room. Absorption, that is the difference between NR and TL, where A2 is the area of the receiving room, and S, when we reference this, is the area of the barrier between the rooms. Absorption is assumed to be average. For live rooms, the factor should be lowered by 2 points, and for the dead room, the factor should be raised by 2 points. Recommended background noise level in the receiving room, as reference, Table 8.3.2 might be used in those particular cases. Sound amplification systems in Section 3.8 are defined and required here. Section 3.8.1.1 refers us to a well-designed sound amplification system should augment the natural transmission of sound from source to listener with adequate loudness and diffusion. It should never be used as a substitute for good building acoustic design because it rarely overcomes or corrects any serious deficiency. Rather, it may amplify and exaggerate the deficiency. We have Section 3.8.1.3 that provides requirements regarding spaces seating less than 500. Should not be required to provide any sound amplification system if it is properly designed, since a normal speaking voice can maintain speech level of 55 to 60 dBA in this volume of space. Controlling noise. Controlling measures shall be taken against noise coming from outdoor and indoor sources as specified in Section 3.4 and 3.5, as we discussed previously. This Section 3.9.1 mandates that, again, space layout, quiet and noisy quarters shall be grouped and separated horizontally and vertically from each other by rooms or spaces, not particularly sensitive to noise, such as entry, door, staircase, corridor, wall closets, or other built-in building components. Bedrooms shall be located in a relatively quiet part of the building. Measures should be taken to avoid transmission of footstep noise through floors. These sections bring out the responsibility of the designer to provide adequate, quiet spaces for these areas within our buildings. Sound insulation factors required by Section 3.9.3, Grade 1 criteria apply mainly to fully residential, quiet rural and suburban areas, and in certain cases to luxury apartments or to dwelling units above the 8th floor of a high-rise building. Grade 2 criteria apply to residential buildings built in relatively noisy environments, typical of urban or suburban areas. Last, Grade 3 criteria express minimal requirements applicable to very noisy locations, such as commercial or business areas, like shop houses with dwelling units on the upper floors or downtown areas. Among the above three categories, Grade 2 covers the majority of residential constructions and therefore shall be regarded as a basic guide. As we saw in previous tables, Grade 2 was indicated in the tables, and if we had to make different modifications, we either added or subtracted values within the tables. Continuing with sound insulation factors, an STC rating of not less than 45 dB is to be provided in walls and floors of residential buildings, between dwelling units of the same building, and between a dwelling unit and any space common to two or more dwelling units. Reduction of airborne noise transmitted through the structure. Exterior walls shall be rigid and massive and must have good sound insulation characteristics, as with few openings as possible. Windows with acoustic louvers might be used to protect noise intrusion while allowing ventilation. The floor of a room immediately above the bedroom or living room shall satisfy Grade 1 impact sound insulation. Regarding outdoor noise, Section 3.10.1.1 requires that measures be taken in planning and design to control noise from external sources mentioned in Sections 3.4 and 3.5. Section 3.10.1.2, the following sources of indoor noise shall be taken into consideration. Any indoor sources, such as indicated in Item A, wood and metal workshops, machine shops, technical as well as engineering testing laboratories, other machine rooms, typing areas, etc., which produce continuous or intermittent noises of disturbing nature, must be taken into consideration, as well as music rooms indicated in Item B. Item C, assembly halls, particularly those which are attached to the main building. Item D, practical workspaces such as practical workspaces, gymnasiums, and swimming pool areas. Item E, school kitchen and dining spaces. And finally, Item F, entry lobby, foyer, lounge, corridor, and other circulation spaces. Planning and design requirements are given to us in Section 3.10.2. Site planning. The school building shall be located as far away as possible from the sources of outdoor noise, such as busy roads, railways, neighboring marketplaces, or adjacent shopping areas, as well as industrial, small-scale manufacturing concerns. Activities and space layout is a planning and a design requirement. The minimum requirement for sound insulation in educational buildings shall be as specified in Table 8.3.5. This particular section, of course, deals with educational, B, occupancy B, and C, institutional buildings when referenced. Last, halls and circulation areas. The lobby, lounge areas, etc., or other circulation spaces and linking corridors shall be separated from teaching areas, lecture galleries, or laboratories. No direct window openings shall be placed along the walls of the corridors or circulation areas. Healthcare buildings, occupancy D. Section 3.11.1.1, outdoor noise. Sources of outdoor noise specified in Section 3.4 shall be taken into consideration for planning and design. Additionally, healthcare service facilities like ambulance, medicine, and equipment vans, store deliveries, laundry and refuse collection trolleys are also frequent sources of noise. Healthcare buildings shall be sited away from such sources as far as practical. Section 3.11.22, Activities and Space Layout. The following points might be given due consideration in the planning and design of healthcare buildings. Long corridors might be avoided, as it may freely spread noise. Mechanical plants might preferably be placed in separate buildings. These are good design techniques to be followed for sound transmission ratings that may cause undue noise within the buildings. Section 3.11.2.3 provides requirements for noise reduction in the sensitive area. In healthcare buildings, many sensitive areas such as operation theaters, doctors' consultation rooms, intensive care units, and post-operative areas shall be provided with special noise control arrangements. These rooms shall preferably be isolated in locations or even corners surrounded by other intermediate zones, which ensure protection of the core area from outdoor noise. A sound reduction of about 45 dBA between the consulting and the waiting room shall be provided in order to weaken the transmission of sound. A lobby-like space in between the interconnecting and communicating doors shall be provided. Section 3.11.2.4, Sound Insulation Factors. We have the rooms and indoor spaces of a healthcare building that must be treated with sound absorptive materials. Different STC ratings of walls specified for separate components of buildings shall have to be considered as follows. For airborne noise, the average STC rating of wall and floor shall be 50 dB. An STC rating of 55 dB shall be required when rooms whose occupants are susceptible to noise. Last, all doors shall be fitted with silent closers. Doors to opposite rooms might be positioned in a staggered manner. Section 3.12, Occupancy I Assembly. Indoor noise regarding Section 3.12.2.2 indicates the following indoor noise sources shall be taken into account in planning and design. Noise from other adjacent halls located within the same building used for similar performance or for seminar, symposium, or general meetings. Noise produced from ticket counters, lobby or lounge areas, rehearsal rooms, even waiting areas and corridors. Noise generated from other ancillary services located within the building, like cafeteria or snack bar, tea shop, post office, bank, or the like. Noise generated from the mechanical or electrical equipment, even air conditioning plants, ventilation channels and ducts, plumbing and water lines, etc., must be taken into account regarding the planning and design of assembly occupancies. The sound insulation factors regarding assembly. Section 3.12.3.4 provides requirements for rooms in the buffer zone, such as lobbies, vestibules, circulation areas, restaurants, counter and issue desk corners, and offices, etc. Shall have sound-absorbing ceilings and carpeted floor. If the rooms are to be used for the purposes of verbal instructions only, a moderate degree of sound insulation, STC 40 to 45 dB shall be accomplished by the movable partitions. If audio equipment or loudspeakers are to be used, an acoustically more effective, efficient partition system shall be used with the sound insulation of STC 45 to 50 dB. An insulation of STC 50 to 60 dB shall be provided if any section of the space is selected for the performance of live music. As you can see that the STC ratings go up when we have this type of live music. All windows shall have to be eliminated from the main auditorium walls in order to exclude excessive outdoor noises. These are good design criteria to follow with respect to rooms in the buffer zone in the assembly occupancies. Continuing with our sound insulation factors, in order to increase the effectiveness of the suspended ceilings, the following measures shall be taken. The ceiling membrane shall weigh not less than 25 kilograms per meter squared. Gaps between ceiling and surrounding structure shall be sealed. The airspace between ceiling membrane and structural floor shall be increased to a reasonable maximum. An absorbent blanket is to be used in the airspace above the ceiling. This would provide plenty of sound deadening materials to slow the transmission or absorb fully the transmission of sound within the space to an acceptable level. Section 3.13, Occupancy E, Business, and F, Mercantile Buildings. Section 3.13.3.3, Noise Reduction in Sensitive Areas. Open plan offices that are seen majorly today indicate the floor area may be carpeted in order to absorb airborne noise and footstep noise as well. The carpet shall preferably be thick and placed on top of resilient floors, as this would be an additive effect. A highly sound absorptive ceiling with a sound absorption coefficient of 0.70 shall preferably be used to absorb 70% of the sound energy, reflecting 30% of it. Noisy office equipment shall be concentrated into specific areas of the office space. These may be like printing machines and other business machines in the office. The space shall be treated with a maximum amount of sound absorptive material and visually separated from the rest of the office. The airspace between the ceiling membrane and the structural floor shall be increased to a reasonable maximum. Reduction of noise at source. The following measures shall be undertaken to reduce noise at source depending on the degree of noise reduction desired. The noise slamming of doors shall be reduced by fitting automatic quiet action type door closers. Continuous soft, resilient strip set into the floor frames as well as quiet action door latches shall be used. Machines like typewriters, calculators, printers, etc. shall be fitted or installed with resilient pads to prevent the floors or tables from acting as large radiating panels, of course from the vibration and being attenuated to the other structural parts of the building. Noises from ventilating spaces, from a uniform flow of traffic, or from general office activities shall be considered to generate an artificial masking noise. Regarding industrial buildings, this is covered in Section 3.14, Occupancy G. Hearing damage risk criteria is specifically covered in Section 3.14.2. This section gives us the requirements when the sound level at a particular section in a factory or industrial building exceeds the specified level in terms of magnitude and time, as shown in Table 8.3.5. Again, we need to reference back to that table for those values. Feasible engineering control shall be applied and implemented in order to reduce the sound to the limits shown. Personal hearing protection equipment shall be provided and used if such control fails to reduce sound levels. Interference with communication. Section 3.14.3. In industries where the operator has to follow verbal instructions during operation of the machine, the background noise shall be reduced to an acceptable level. In all cases, precautionary measures shall be taken so that the noise generated inside may not be the cause of accidents by hindering communication or by masking warning signals. Noise reduction by enclosures and barriers. Specific reference here is Section 3.14.4.2. When the plant is large, in which the overall noise level results from many machines, an enclosure shall be provided. When only one or two machines are the dominant source of disturbing noise, the noisy equipment shall be isolated in small area of enclosure. The enclosure shall be in the form of close-fitting acoustic box around the machines. The box shall be of such character that the operator can continue with his normal work outside the box. If the size of the machine is large and asks for more working space, thus not permitting close-fitting enclosures, the machine shall be housed in a separate room or enclosure. The inside of the enclosure shall be lined with sound-absorbing materials in order to reduce the contained noise. This is the end of the presentation. Thank you for your participation.